Swayam Prabha. Digital India. Educated India.
Okay, so we have so far seen some fundamental elements of how we can really classify certain set of variables using a decision surface, especially in the case where the points are linearly separable. Okay. So, now we have to see whether the same thing is possible using the neural network. All right. So, we are going to be applying a similar principle and then show later that it is possible to do the linear separation using a perceptron. Okay. So, before that, as very simple and a brief introduction related to the neural network that we have. Okay. So, this is the biological neural network, this is the real one, and the artificial neural network is supposed to copy some aspects of what happens inside the brain. Okay. So, this is a very complex mechanism we know very well. Think about that poor kid, right, who is trying to recognize the faces of so many people even at the very young age without any input parameters provided. So, you remember that, right. So, in this case we estimated the complex function classifier based on the input and the class that is given. So, what we are providing to the kid is only this. So, unfortunately, the kid has to do the whole thing, correct. Our brain is so wonderful, and it is a, I do not know whether you can call it as a machine, it is a beautiful set of biological pieces that gives you the ability to do lots of things, and we are trying to see how those things could be taught to the machines, step by step. And a very simple implementation of what happens inside our brain is done through the current neural net models and so on. So, for that we need to understand a little bit about what is there in the biological neural network, and then move to the artificial one. Okay. So, this is a neuron and it has several dendrites coming in which are providing the inputs. Okay. And then the incoming signals are coming through the synapse, and then we have one axon that is like an output function that carries the electrochemical signals between neurons. Okay. So, that is what we have. So, in this case there is an input that is coming in, and the electrical signals are carried between one neuron to the other through axons. Okay. And there are plenty of them in the brain. So, in this case you will have a similar structure of this on this side too, and here, here, here and so on. There are plenty of them. So, each neuron can form thousands of links with the electrochemical connections between neurons are not static, they keep changing. Okay. More signals sent between two neurons, the stronger the connection grows with each new experience and each remembered event, the brain slightly rewires the physical structure. So, every time the more signals that are sent between the connections, the strength starts to increase. The smell of a coffee really triggers a lot of events. Think about that, right. So, how many times you smell a coffee and then think, oh okay, this is something that I have experienced when I was in my grandma's house. So, and then suddenly the the house where your grandma lived, and then the surrounding, the garden, the people that you had met there, and all those things starts coming into you, right. Because of that connection is pretty strong, you start remembering so many things. I am just quoting one example. For so many other people, some other event could trigger a lot of chain of thoughts. Okay. And we keep learning every time. The strengths of the connections are increased every time based on how many ever times reinforce that connection. Now, a little bit about some of the associative laws which are very useful in the design of neural networks. So, one is the law of similarity. So, these laws are fundamental laws attempted by Aristotle. It is very old. So, in terms of learning and memory, there are 4 fundamental laws. One is the law of similarity, the second one is the law of contrast, third is contiguity, and then fourth is the fluency. So, we also have to relate this to what we have in the natural language processing, then only they are useful, otherwise it is at another individual set of laws. Okay. If two things are similar, the thought of one will tend to trigger the thought of the other. Okay. This is something that I am going to be talking about in future, word to wake. But let us talk about the LSI that we have already learned. So, what does LSI do? Using the SVD, it is able to really decompose the term document matrix into 3 matrices, right. So, one is the left singular matrix, we called it as U, and then we have a diagonal matrix where the elements are in the descending order, it is the singular matrix, and then another one which is a V, this is the right singular matrix. And we mentioned that the elements or the rows of U represent the words, right. So, it is equal to the size of the terms that we had. For example, if the term, so for the want of space I will use this. This is your document, right. So, the column tells you various features of your documents, and then rows gives you the features of your words. And then we mentioned that after transforming the original matrix into this latent domain, the rows of U represent the word vector. It is not the representation of the term directly, but it represents lot of similar words as part of that. That is why we call that as the word embedding. So, in the same fashion, the laws of similarity, when you use one of these techniques, either LSI or word to wake, we are able to capture the similar pattern. So, if you take one of the vectors, it should be able to tell you what are all other similar words that you have, okay, related to the word that you have picked up. So, we will show one example later. During the time this will become very clear. Okay. So, in this case, if you recollect or if you pick one word, the context related to the word is learned using the LSI as well as in the word vector that we will be talking about later. So, it will be able to tell you what are all the related words with respect to some cosine distance. So, this is very useful in the natural language processing, where we can pick up the similar words with respect to its context. In another example, if you recollect the birthday of your friend in the class, and you are celebrating it So, immediately the thought will come, okay, whose birthday is next, right. So, that is something we can roughly relate to law of similarity. And then the law of contrast, seeing or recalling something may also trigger the recollection of something which is completely opposite. Okay. So, in some way we are able to find, instead of the similarity, the antonyms of each word. For example, I have trained the network in such a way that when you give one word, it will always give me the opposite of that words, or the words that are opposite to that. Okay, so, that could be the law of contrast. Law of contiguity, things or even that occur close to each other in space or time tend to get linked together in the mind. Okay, so, that is a funny example that I have quoted here, but I think it is true in many cases. This is one simple example. So, while walking back to your house, when you find a snake in one corner of the street today, right, and then if you are going to the same place every day from today onwards, you always tend to look into that corner to see if you can find a snake again. Okay. So, this you will call as the law of contiguity. And then law of frequency is something we spoke about even in the prediction of the next word, right. If certain set of words are connected through the context and its frequency is pretty high, when you provide the first word, it is able to tell you what could be the next word based on the frequency of the occurrences of those two words in the corpus. So, again the law of frequency is very useful in this case. So, if you look at this, these are all patterns that we can use as part of the input to the system, right. So, we should be able to capture for example, the similarity words. So, in the case of word to vec, that is how we really train the network. So, we have a set of context, and then I want to find out the middle word given the surrounding word. I would use the laws of similarity. The patterns are found using the laws of similarity. Okay. The prediction of the next word or the probability of a given sentence could also be found using the law of frequency. Okay. So, there is some association, even though it is pretty old, we are able to map these patterns into, or these laws into our existing problem in hand. Okay. So, what are the differences between the perceptrons? We are going to be calling the artificial neuron as the perceptron. It is biological and perceptron is a mathematical model. Here dendrites receive the electrical signal, perceptrons receive the values as input, electrochemical signals between the dendrites and the axon. So, whereas we are going to have, again there are certain weights, for example, in the case of the perceptron, let us say this is your neuron, we are going to be connecting with respect to some weights. Okay. So, the strength of the signal is represented by these weights. In the same way we had seen in the biological neuron. The electrochemical signals are not static. We keep learning, so they are not very static. Even in this case, during the training process, these weights keep changing. Once the training is complete, the weights are static. Okay. So, I am going to give you a very high level overview of what a perceptron is and what we can do with that using this simple architecture. So, in this case we have a set of inputs, or we can call it as the feature vectors, whose size is h x1 to x. Okay. And then we have a bias whose value is plus 1, which is connecting to the perceptron using the weights W naught. So, all the input feature vectors are connected to this element through the weights. Okay. So, we call them as weights. So, the input is connected to the neuron through the weights. So, for the sake of explanation, I have actually divided this into two spaces. One is the activation functions. Once the values are received, okay, they are summed in this neuron, they are linearly summed, and then there is some value that you have obtained. Okay. So, for example, the value could be between -5 to +5, okay, depending on the weights that you have used as the weight that are connecting the input and the neuron. So, we want to actually translate the values between 0 and 1 or -1 and 1 or through some probability distribution where the values when they are summed would be equal to 1. So, there are so many ways we can do that. So, the activation function what it does is it smashes the values of this into a point in this space. See, for example, if I have -5 and then the value becomes using the activation function, it gives you 0.01. Okay, and my threshold, let us say my threshold is 0.5. If the threshold is greater than 0.5, then the value is equal to +1, otherwise it is going to be -1 as given by this decision function. So, the activation function squashes the value between 0 and 1, and the decision function actually looks at the value squashed by the activation function and then makes a decision whether to provide +1 to it or -1 to it depending on the threshold that we have set up. So, we have the feature vectors coming in into the neuron and then the weights are connecting the input and the neuron. There is an activation function that smashes the value between two values, and there is a decision function that translates the activation function value into two different values which we can use. Take the case of the sentiment analysis. Assume that we are able to provide the input to the perceptron using a one hot vector. Remember one hot vector, and the index of that particular element in that space will give you the word. For example, if it is the 10th element and my positive value is good. So, it will represent good. So, in this fashion I can keep feeding the feature vectors as input, and the result would be expected as either positive or negative. So, for this I expect the perceptron to output as +1, okay, and then for bad I expect the perceptron to output as -1, and then the activation function, it smashes the value between 0 and 1, and then the decision function decides whether it is a positive or negative depending on the value it received from the activation function. Okay. So, this is a very simple network that you have for perceptron. Again, the mathematical operation that we are going to be performing here are very simple. So, one is we have a bias that is connecting to it. So, the sum that you are looking at here would be x 1 w 1 plus x 2 w 2 to x n Wn, or it is written in a very simple notation. It is a sum of I equal to 1 to n Wi xi. So, this is a simple dot product that you have, and then you finally add that with the bias and then give it to the activation function. We will talk about what that activation function is. When you provide the value computed to the activation function, it maps it between two values. Let us say it is going to be mapping it between two values, and these are all real values. And then based on what the value is, the decision function either outputs +1 or -1 depending on what value this activation function has provided. Okay. So, it is a very simple mathematical model, and I want you to go and then take a look at NumPy. So, a lot of linear vector operations or rather linear algebraic operations are performed in this library NumPy, and you can very easily translate this into NumPy and do it instead of writing loops of instructions to add this. You can just use one single instruction to say np dot like this. Okay. So, this is clear now. The input could be anything, right. So, it could be any real values, or it could be a one hot vector in the case of the natural language processing. The output is going to be only two values, either +1 or -1 depending on what activation function squashes. Okay. So, it is a very simple example of a perceptron where there is only one element, and this is good enough to linearly classify set of vectors into two regions. Okay. So, how do we teach the perceptron, or how does perceptron learn the weights? So, very simple, it is going to learn the weights. The weights are going to be your model. So, the first statement is it learns the weights. Let us see how it learns the weights. They are adjusted until the output is consistent with the target output in the training examples. So, you keep changing the weights in such a way that the estimated output is very close to the target output. Since we know the relationship between the input vectors and the output vectors, we are estimating the model, and the model parameters are here W and W naught. W is the weight connecting the input and the perceptron, and W naught is the weight connecting the bias and the perceptron. Okay. So, if we have iteration going from 1 to k, right. So, we need to keep identifying the weight that you want to update, and this weight is proportional to the new weight that you are going to be using to update the weights connecting the input and the perceptron is proportional to the error that is computed. This is your target and this is your estimate. So, intuitively you can very easily say that the next weight is given by, or the new weight is given by the old weight, and there is one new parameter that I have here, and here we have the error and the input that is connecting. Okay. The parameter that we have here is called the learning parameter. The eta is the learning parameter, and it is adjusted to actually help you discern. if the eta value is very high, the learning jumps in this fashion. If the eta is very small, it slowly and steadily reaches this. Normally we do some kind of an estimation for this, by looking at the training sample and then see how the weights are adjusted and how the errors are jumping from one point to the other during the iteration. We keep adjusting this. Okay, so we look at the way the training goes and adjust this and then finally settle down to some number. So, until then we empirically change these values. Okay. So, the eta parameter is updated based on the experience that you gain in the model estimation. So, normally it ranges from 0.1 to 0.01. Okay, rarely it goes below this point, and you can't just have eta equal to 1, 2 and so on. It will be very drastic. For example, if you have the error surface in this fashion and if you have a big eta, it might go wild in this fashion. It is very difficult to control that. So, ideally it should descend in this fashion. Okay. So, it is very crucial to really set the right parameter for the eta. So, when y minus y hat equal to 0, that means there is no, I would say approximately equal to 0, there is no prediction error. So, that is when we normally set this to 1 into e power minus 5. It is a very small value. So, during the training, the weights contributing most to the error require adjustments. Okay. So, I am going to ask you to do one exercise in this, where supposing if my output or the target output is 1 and the estimated output is minus 1. Okay. So, this is the estimated one, this is the target value. Okay. So, when you have this set, so how will you update W? So, what is the kind of adjustment you make to W so that it becomes closer to 1. So, right now it is minus 1. So, when you do this operation, the error equal to 2. So, in which direction you update the weights? Okay, this is a question for you. I like you to go and then refer some books and figure out what could be the adjustment that you want to make. So, we know that we need to make some adjustment, but what kind of adjustment? So, same example, I am sorry, another example would be target is minus 1 and y hat is 1. In which way you would adjust the weights, either increase the weights or decrease the weights by a certain fashion. We know that it is proportional to the error, right. In which way you would move the weights. Okay. So, this is a very simple algorithm to the perceptron. Let us assume that we have about k vectors, and then there are n number of features that we have for each the vector, and then we have set the learning parameter to be 0.01, and then epoch count is t equal to 1 and j equal to 1. So, I have used a new word epoch here. The epoch is one complete presentation of the data set. For example, we have let us say we are going to be doing the sentiment analysis, where we have words representing the one hot vector, right. So, we have about 500 words that we want the system to learn, either to be as positive words or negative words. I am providing one hot vector okay. So, about 500-600 of them. So, they represent 1 there. Take every word, compute the error, make the change until it satisfies the input output relationship, and then take the next word and keep going. So, that is one way. In this case, I am presenting the entire 600 one hot vectors in one go, not in one go, one after the other, and then start making the adjustment every time. Okay. So, this is one epoch. This is one way of presenting the data set. We initialize the weights with the random numbers, initialize the input layer with the first data, and calculate the net output using this relationship, calculate the error, update the weight based on this equation, okay. Then repeat steps 1 through 9, or rather 7 through 9, until the error is less than a given threshold or predetermined number of epochs are completed. Okay. So, these are the 10 steps that you have to make the perceptron learn. So, again this is for you to find out what is the optimal eta size. Should it be big or small or very small or very big. Okay. Okay, so in this session we are going to be talking about the activation function. We spoke about the activation function in the perceptron case, where we mentioned that it will output a value between 0 and 1 or -1 to 1, or it gives you a probability distribution where the sum of each element would be equal to 1, right. So, let us see each one of them. There are several types of activation functions. One is the Hart threshold, second one is a sigmoid, third is a hyperbolic tangent function, and then fourth one is a rectified linear unit, and then there is another one called leaky ReLU, and the popular one in the natural language processing world is the softmax, which is usually used at the output layer, and the sigmoid and tanh are usually used in the middle layers. Okay. So, there are network architecture where there would be more than one neural element. Okay. So, you will have input connecting to neurons in this fashion, and you will also have multi-class output in this fashion. Okay. So, in most cases of the natural language processing, you will have a minimum of 3, let us say 3 layers. We call this as the input layer, hidden layer and the output layer. in many neural networks you will find that the hidden layers are squashed using either sigmoid or tanh, and then the output is squashed by a softmax.